Creating an index for a data engineering topic can be quite broad, but here's a list of key topics you might consider including in an index for a data engineering reference. Data ingestion is the process of collecting, importing, and transferring data from various sources into a storage or processing system, where it can be analyzed, stored, or transformed for further use. This is a fundamental step in the data management and analytics pipeline, especially in the context of big data and data-driven decision-making. Data can come from a wide range of sources, including databases, logs, external APIs, files, streaming data sources, and more. Here are some key aspects of data ingestion. 1. Data sources Data can originate from various sources such as databases, SQL or NoSQL, files, CSV, JSON, XML, web APIs, sensors, social media feeds, or even live data streams. 2. Data collection Data ingestion involves mechanisms for collecting and capturing data from these sources. This can be done through batch processing or real-time streaming, depending on the nature of the data. 3. Data transformation In some cases, data needs to be transformed or cleaned during the ingestion process to ensure its quality and compatibility with the target system. This may involve data normalization, data enrichment, or data cleansing. 4. Data validation It's essential to validate the incoming data to ensure it adheres to the expected format, schema, and quality standards. Invalid data may be rejected or logged for further investigation. 5. Data integration Data from different sources often needs to be integrated and consolidated into a single dataset or data warehouse for analysis. Integration may involve merging, joining, or aggregating data. 6. Data loading Once the data is prepared, it's loaded into a storage system such as a data warehouse, data lake, or a database for further processing and analysis. 7. Real-time versus batch ingestion Data ingestion can be done in real time, streaming, or in batches. Real-time ingestion processes data as it arrives, while batch ingestion collects and processes data at scheduled intervals. 8. Scalability and reliability Data ingestion systems need to be scalable to handle large volumes of data and reliable to ensure data is not lost during the process. 9. Monitoring and management Continuous monitoring and management of the data ingestion process are crucial to detect and address issues such as data delays, failures, or data quality problems. Tools and technologies used for data ingestion can vary widely depending on the specific requirements of a project. Common tools include Apache Kafka for real-time streaming, Apache Niffy, Apache Flume, AWS Glue, Apache Spark, and various ETL, extract, transform, load, tools. Effective data ingestion is a critical step in the data lifecycle, as it lays the foundation for data analysis, reporting, and other downstream processes, ultimately driving insights and decision-making in organizations. Data storage is a critical component of data engineering, which is the field of designing and managing the infrastructure and systems for collecting, storing, processing, and analyzing data. Proper data storage is essential for ensuring data integrity, availability, and scalability. Here are some key aspects of data storage in data engineering. Data warehouses. Data warehouses are centralized repositories that store structured and sometimes semi-structured data from various sources. They are designed for analytical and reporting purposes, allowing for complex queries and aggregations. Common data warehouse solutions include Amazon Redshift, Google BigQuery, and Snowflake. Data lakes. Data lakes are storage repositories that can store structured, semi-structured, and unstructured data in its raw form. They are designed for storing vast amounts of data, including data that may not have a predefined schema. Popular data lake technologies include Amazon S3, Azure Data Lake Storage, and Hadoop HDFS. Relational databases like MySQL, PostgreSQL, and Microsoft SQL Server are used for storing structured data with well-defined schemas. They are often used in transactional systems and as sources for data warehouses. NoSQL databases, such as MongoDB, Cassandra, and Redis, are used for handling unstructured or semi-structured data and for scenarios where high scalability and flexibility are required. Distributed file systems like Hadoop Distributed File System, HDFS, and distributed object stores like Amazon S3 provide scalable and fault-tolerant storage solutions for big data applications. In-memory databases like Redis and Memcached store data in RAM, enabling very fast data access. They are often used for caching and real-time data processing. Columnar databases like Apache Cassandra and Apache HBase are optimized for read-heavy workloads and are commonly used for time series data or data with a large number of columns. Key-value stores like Redis and Amazon DynamoDB store data as key-value pairs and are often used for caching and low-latency applications. Data partitioning and sharding. Large datasets can be partitioned or sharded across multiple storage instances to improve performance and scalability. Each shard contains a subset of the data, and these shards can be distributed across multiple servers or nodes. Data compression and encryption. Data storage solutions often employ compression to reduce storage costs and encryption to ensure data security and compliance with regulations. Data backup and disaster recovery. Implementing robust backup and disaster recovery strategies is crucial to ensure data availability and business continuity in case of failures or disasters. Data lifecycle management. Managing the lifecycle of data includes defining retention policies, archiving, and eventually purging or deleting data that is no longer needed to optimize storage costs and compliance. Metadata management. Properly cataloging and managing metadata about stored data is essential for data discovery, lineage, and governance. Data quality and data governance. Ensuring data quality and adhering to data governance policies is crucial in data storage to maintain data accuracy and compliance with regulations. Scalability and performance. Choosing the right data storage solution and optimizing its configuration is essential for meeting performance requirements as data volume and velocity grow. Data engineers need to select the appropriate data storage solutions based on the specific needs of their organization, considering factors like data volume, data variety, data velocity, budget constraints, and performance requirements. Additionally, they must design and maintain the storage infrastructure to ensure data is accessible, reliable, and secure for downstream analytics and applications. Data transformation is a crucial process in data engineering that involves cleaning, enriching, and restructuring raw data to make it suitable for analysis or storage in a data warehouse or data lake. Data transformation is a fundamental step in the extract, transform, load, ETL process, where data is extracted from various sources, transformed into a usable format, and loaded into a target system. Here are some key aspects of data transformation in data engineering. Data cleaning. Data often contains errors, missing values, duplicates, and inconsistencies. Data engineers must clean the data by removing or imputing missing values, identifying and eliminating duplicates, and standardizing data formats. Cleaning ensures that the data is accurate and reliable. Data enrichment. Sometimes, data needs to be enriched with additional information from external sources to make it more valuable. For example, adding geographic coordinates to addresses or merging data from multiple sources to create a comprehensive dataset. This process can involve using APIs, data integration tools, or custom scripts. Data aggregation. Aggregation involves summarizing and condensing data to a coarser granularity. It often includes operations like grouping data by a specific attribute and calculating aggregate statistics, example, sum, average, count, for each group. Aggregation is useful for creating reports and dashboards. Data transformation logic. Data engineers write scripts or use ETL tools to apply specific transformation logic to the data. This logic can include filtering rows, calculating derived columns, converting data types, and applying business rules. The choice of programming languages, example, Python, SQL, or ETL tools, example, Apache Spark, Talend, depends on the complexity of the transformations. Data joining and merging. Combining data from multiple sources is a common transformation task. Engineers use techniques like SQL joins or merging operations in Python or other programming languages to combine datasets based on common keys or attributes. Data normalization and denormalization. Normalization involves organizing data into a structured format with minimal redundancy, while denormalization combines normalized data into a more accessible form for analysis. The choice between normalization and denormalization depends on the specific use case and database design. Data validation. Data engineers implement validation checks to ensure data quality and integrity. This may involve verifying that data adheres to predefined rules, constraints, or reference data. Data deduplication. Eliminating duplicate records is crucial to maintain data quality and prevent inaccuracies in analysis. Techniques such as hashing and matching algorithms can be used to identify and remove duplicates. Data partitioning and bucketing. In distributed data processing systems like Hadoop or Spark, data may be partitioned or bucketed to optimize query performance. This involves dividing large datasets into smaller, manageable chunks. Data compression and serialization. To optimize storage and processing efficiency, data can be compressed and serialized into formats like Parquet, ORC, or Avro. These formats are often used in data lakes and data warehouses. Data masking and anonymization. When dealing with sensitive or personally identifiable information, PII, data may need to be masked or anonymized to protect privacy and comply with data protection regulations. Data transformation is a highly iterative and customizable process that depends on the specific requirements of the data pipeline and the analytical goals of the organization. It plays a critical role in ensuring that data is accurate, consistent, and ready for analysis by data scientists, analysts, and other stakeholders. Data processing in data engineering involves the collection, transformation, and analysis of data to extract meaningful insights. Real-time data processing is particularly important for applications that require immediate responses or decision-making based on the most up-to-date information. Here's a real-time example of data processing in data engineering. Example: e-commerce website. Imagine you are working for an e-commerce company, and your role is to ensure that product recommendations for users are continuously updated in real time as they browse the website. To achieve this, you need to process user interactions and update product recommendations instantly. Here's how the data processing pipeline might work. Data collection. User interactions on the e-commerce website are continuously collected. This includes actions like product views, adding items to the cart, and purchases. These interactions generate real-time data streams. Data ingestion. The incoming data streams are ingested into a real-time data processing system. This could be a streaming platform like Apache Kafka or AWS Kinesis. Data transformation. Once the data is ingested, it needs to be transformed into a format suitable for analysis. In this case, you might aggregate user behavior data to understand what products are popular, calculate user preferences, and update user profiles in real time. Real-time analytics. Real-time analytics engines like Apache Flink or Apache Spark Streaming can be used to process the data streams. These engines allow you to run complex queries and calculations on the data as it arrives, providing immediate insights. Machine learning models. To generate product recommendations, machine learning models can be employed. These models take into account user behavior, preferences, and historical data to recommend products in real time. Recommendation updates. As new data arrives and user behavior changes, the recommendation models are continuously updated. The real-time data processing pipeline ensures that the recommendations are always based on the most recent data. User feedback. Users may provide feedback on the recommendations, and this feedback is also collected in real time. It can be used to further refine the recommendation models. Presentation. The updated product recommendations are presented to the user on the website in real time. This can be done through personalized recommendations sections or pop-ups. Monitoring and scaling. The data processing pipeline must be monitored for performance and scalability. If the website experiences a sudden surge in traffic, the system should automatically scale to handle the increased load. Data storage. In addition to real-time processing, the processed data can be stored in a data warehouse or database for historical analysis, reporting, and business intelligence. In this example, real-time data processing ensures that the e-commerce website provides relevant and up-to-date product recommendations to users as they browse, ultimately improving the user experience and potentially increasing sales. Data modeling is a crucial step in the process of designing a database or information system. It involves creating a conceptual representation of data to understand how data is organized, related, and stored within a system. Let's explore data modeling with a real-time example. Scenario. Imagine you're tasked with designing a data model for an e-commerce platform that sells products online. The goal is to create a database schema that can efficiently store and manage information about products, customers, orders, and reviews. Steps in data modeling. Identify entities. The first step is to identify the main entities or objects in your system. In this e-commerce example, common entities include product, customer, order, review. Define attributes. For each entity, define the attributes or properties that describe it. For example, product entity might have attributes like product ID, name, price, description, and stock quantity. Customer entity might have attributes like customer ID, first name, last name, email, and address. Establish relationships. Determine how these entities are related to each other. In this case, an order is associated with one or more products and one customer. So, you establish a relationship between order, product, and customer entities. A review is related to a specific product, so you establish a relationship between review and product entities. Normalization. Apply normalization techniques to minimize data redundancy and improve data integrity. For instance, separate information into different tables to prevent duplicate data. Create diagrams. Use visual tools like entity relationship diagrams, ERDs, to represent the relationships and attributes of your entities. ERDs help you visualize the structure of your data model. Data types and constraints. Specify data types, example, integer, varchar, date, and constraints, example, unique, primary key, foreign key, for each attribute in your data model. Implement. Once you have your data model design, you can implement it in your chosen database system, example, SQL, NoSQL. Data quality is a critical aspect of data engineering, as it directly impacts the reliability and usefulness of data for analysis, reporting, and decision-making. Ensuring high data quality is essential to maintain the integrity of data throughout its life cycle, from its collection and storage to its transformation and consumption. Here are some key considerations and practices related to data quality in data engineering. Data profiling. Data engineers often begin by profiling data sources to understand their structure, content, and quality. Profiling helps identify issues like missing values, outliers, and inconsistencies. Data cleaning. Data cleaning involves the process of identifying and rectifying data errors and inconsistencies. Common cleaning tasks include handling missing values, removing duplicates, correcting typos, and standardizing data formats. Data validation. Data validation ensures that data adheres to predefined rules and constraints. It involves checking data against predefined validation rules to identify any anomalies or violations. Data transformation. During data transformation, data engineers often apply various operations to prepare data for analysis. This can include aggregations, filtering, joining, and data enrichment. Ensuring the quality of transformed data is crucial to prevent downstream issues. Data quality metrics. Define and measure data quality metrics that are relevant to your organization's needs. Common data quality metrics include accuracy, completeness, consistency, timeliness, and reliability. Data governance. Establish data governance practices and policies to ensure data quality is maintained over time. This includes defining data ownership, access controls, and data stewardship responsibilities. Data quality tools. Utilize data quality tools and frameworks to automate data quality checks and monitoring. These tools can help identify and address data issues in real time or on a scheduled basis. Data lineage. Maintain data lineage information to track the flow of data from source to destination. This helps in identifying where data quality issues may have originated and facilitates their resolution. Data auditing and logging. Implement data auditing and logging to keep records of data changes, ensuring traceability and accountability for data quality. Data quality monitoring. Continuously monitor data quality using automated processes and alerts. Proactively address data quality issues as they arise. Data documentation. Properly document data sources, data transformations, and data quality rules. This documentation helps data engineers and data analysts understand the data and its quality requirements. Data user training. Educate data users, including analysts and data scientists, on data quality best practices and how to interpret data quality metrics. Data quality improvement. Establish a feedback loop for data quality improvement. When issues are identified, prioritize and implement corrective actions to prevent similar problems in the future. Data quality culture. Promote a culture of data quality within the organization, emphasizing the importance of data accuracy, consistency, and reliability in decision-making. By addressing these aspects of data quality in data engineering, organizations can enhance the value of their data assets and make more informed decisions based on trustworthy data. Data integration is a critical component of data engineering, which focuses on collecting, processing, and managing data to make it accessible, reliable, and useful for various business purposes. Data integration involves combining data from multiple sources, transforming it into a consistent format, and then loading it into a target system, such as a data warehouse or a data lake. This process enables organizations to have a unified view of their data and supports better decision-making, reporting, and analytics. Here are the key aspects of data integration in data engineering. Data sources. Data integration starts with identifying and connecting to various data sources. These sources can include databases, APIs, flat files, cloud services, and more. These sources may have different data formats, structures, and protocols. Data extraction. Once the data sources are identified, data engineers need to extract data from these sources. This process involves querying databases, making API calls, or reading files. Tools like Apache Nifi, Apache Scoop, or custom scripts are commonly used for extraction. Data transformation. Data from different sources may not be in a consistent format or structure. Data engineers perform transformation operations to convert and standardize the data. Transformations can include cleaning, filtering, aggregating, joining, and enriching data. Tools like Apache Spark, Apache Flink, or SQL can be used for these tasks. Data quality. Ensuring data quality is essential in data integration. Data engineers need to validate, cleanse, and enrich data to eliminate errors and inconsistencies. Data quality checks and validation rules are applied during this phase. Data loading. After transformation and validation, the data is loaded into a target system, such as a data warehouse, data lake, or a reporting database. The choice of storage depends on the specific use case and requirements of the organization. Data synchronization. In some cases, data integration is an ongoing process. Real-time or near-real-time data synchronization is required to keep the target system up to date with changes in the source systems. Technologies like change data capture, CDC, and stream processing are used for this purpose. Data governance and metadata management. Effective data integration includes managing metadata, which provides information about the data's source, lineage, and meaning. Data governance policies should also be established to ensure data security, compliance, and privacy. Monitoring and maintenance. Continuous monitoring of data integration pipelines is essential to detect and address issues promptly. Data engineers need to maintain and optimize these pipelines as data sources or business requirements change. Scalability and performance. As data volumes grow, data integration processes must be scalable and performant. Parallel processing, distributed computing, and data partitioning techniques are often used to address scalability challenges. Documentation. Thorough documentation of data integration processes, including source-to-target mappings, transformation logic, and data lineage, is crucial for maintaining transparency and aiding troubleshooting. Error handling and recovery. Data integration pipelines should have robust error handling mechanisms to deal with unexpected issues and ensure data consistency. Techniques like checkpointing and retry mechanisms can help in recovering from failures. Overall, effective data integration in data engineering is a complex and iterative process that requires a combination of technical skills, domain knowledge, and a deep understanding of data sources and business requirements. It plays a pivotal role in enabling data-driven decision-making and supporting various analytics and reporting initiatives within an organization. Here is a step-by-step guide to data orchestration in data engineering. Define your data pipelines. This involves identifying the different sources and destinations of your data, as well as the transformations that need to be applied. You should also create a diagram of your data pipelines to visualize the flow of data. Choose a data orchestration tool. There are a number of different data orchestration tools available, such as Apache Airflow, AWS Step Functions, and Google Cloud Data Composer. Choose a tool that meets your specific needs, such as the size and complexity of your data pipelines, the budget, and the skill set of your team. Implement your data pipelines. This involves configuring your data orchestration tool to run the different tasks in your data pipelines. You will also need to write code to perform the data transformations. Test and deploy your data pipelines. Once you have implemented your data pipelines, you need to test them thoroughly to make sure that they are working as expected. Once you are satisfied with the results, you can deploy your data pipelines to production. Monitor and maintain your data pipelines. Once your data pipelines are deployed, you need to monitor them to make sure that they are running smoothly. You should also have a process in place to troubleshoot and fix any problems that arise. Here are some additional tips for data orchestration. Use a modular approach. Break down your data pipelines into smaller, more manageable tasks. This will make it easier to develop, test, and maintain your pipelines. Use version control. This will allow you to track changes to your data pipelines and revert to previous versions if necessary. Use documentation. Document your data pipelines so that it is easy for others to understand and maintain them. Use monitoring and alerting. Monitor your data pipelines to identify and fix problems early on. You should also set up alerts so that you are notified of any problems immediately. Data orchestration can be a complex task, but it is essential for organizations that want to get the most value from their data. By following the steps above, you can implement a data orchestration strategy that will help you to build and maintain reliable, scalable, and efficient data pipelines. Data security is a critical aspect of data engineering, as it involves the collection, storage, processing, and transmission of sensitive and valuable information. Ensuring data security is essential to protect an organization's assets, maintain regulatory compliance, and build trust with customers and partners. Here are some key considerations for data security in data engineering. Access control. Implement strict access controls to ensure that only authorized individuals or systems can access and modify data. Use role-based access control, RBAC, to define and enforce who can perform specific actions on data. Authentication and authorization require strong authentication mechanisms such as multi-factor authentication, MFA, to verify the identity of users and systems. Additionally, implement authorization policies to define what actions each authenticated user or system is allowed to perform. Encryption. Encrypt data at rest and in transit. Use encryption algorithms and protocols like TLS-SSL for data in transit and encryption solutions such as AES for data at rest. This prevents unauthorized access to data even if a breach occurs. Data masking and anonymization. When dealing with sensitive data, consider using data masking and anonymization techniques to replace sensitive information with fictional or masked data while preserving data integrity for testing or development purposes. Secure data transfer. Ensure that data transferred between systems or over networks is done securely. Employ secure file transfer protocols, example SFTP, SCP, and use encryption to protect data during transit. Data classification. Classify data based on its sensitivity. Not all data is equally valuable or sensitive, so prioritize security measures based on the classification of data. Data retention and disposal. Establish clear data retention policies and procedures. Dispose of data that is no longer needed, and do so securely to prevent data leaks. Audit trails and logging. Implement comprehensive logging and auditing mechanisms to track data access and changes. Regularly review logs for suspicious activities and maintain audit trails for compliance purposes. Vulnerability scanning and patch management. Regularly scan systems and applications for vulnerabilities and apply patches and updates promptly to address security flaws. Firewalls and intrusion detection systems. IDs employ firewalls to control network traffic and intrusion detection systems to monitor for suspicious activities. These tools can help detect and respond to security threats in real time. Secure coding practices. Encourage secure coding practices among data engineers and developers to prevent common security vulnerabilities, such as SQL injection or cross-site scripting, XSS, in data pipelines and applications. Data privacy compliance. Comply with data privacy regulations and standards such as GDPR, HIPAA, or CCPA, depending on the nature of the data you handle. Ensure that data engineering processes align with the requirements of these regulations. Incident response plan. Develop an incident response plan to address security breaches or data leaks promptly. This plan should include steps for containment, investigation, notification, and recovery. Security training and awareness. Educate data engineering teams about data security best practices and raise awareness about potential security threats and social engineering tactics. Regular security audits. Conduct regular security audits and assessments to evaluate the effectiveness of your data security measures and identify areas that require improvement. Data security should be an ongoing process, with continuous monitoring and adaptation to evolving threats. It's crucial to strike a balance between data accessibility and security, ensuring that the right people have access to the right data at the right time while protecting sensitive information from unauthorized access or breaches. Data monitoring and logging are critical aspects of data engineering that ensure the reliability, integrity, and performance of data pipelines and systems. These practices help detect and troubleshoot issues, track data changes, and maintain data quality. Here's an overview of data monitoring and logging in data engineering. Data monitoring. Pipeline monitoring. Monitoring data pipelines involves tracking the flow of data from source to destination. This can include ETL, extract, transform, load, pipelines, streaming data, or batch processing. Key aspects to monitor include data ingestion rates, job completion status, and data latency. Error detection. Implementing real-time error detection is crucial to identify issues as they occur. This can involve monitoring for data anomalies, unexpected schema changes, or missing data. Performance monitoring. Measure the performance of data pipelines to ensure they meet service level agreements, SLAs. This includes monitoring CPU usage, memory usage, and network bandwidth to optimize performance. Data quality monitoring. Continuously assess data quality by defining data quality rules and conducting checks. These rules may include data completeness, consistency, accuracy, and timeliness. Alerting. Set up alerts to notify data engineering teams when anomalies or issues are detected. Alerts can be triggered based on predefined thresholds or rules, ensuring quick response to problems. Dependency tracking. Keep track of dependencies between different components and pipelines to understand the impact of changes and failures. This helps in root cause analysis. Data logging. Logging framework. Implement a robust logging framework that captures relevant information about data pipelines and processes. Use structured logging to make it easier to search and analyze logs. Log types. Pipeline logs capture information about each step in the data pipeline, including input data, transformations, and output data. Error logs log errors, exceptions, and warnings to facilitate troubleshooting and debugging. Audit logs record changes to data, such as inserts, updates, or deletions, to ensure data governance and traceability. Centralized logging. Store logs in a centralized location or log management system, such as ELK Stack, Elasticsearch, Logstash, Kibana, or Splunk, for easy access and analysis. Log retention. Define a log retention policy to manage storage costs and compliance requirements. Older logs can be archived or deleted as needed. Security and access control. Ensure that log data is secure and access is restricted to authorized personnel. This is especially important when dealing with sensitive data. Data visualization and dashboards. Dashboards. Create dashboards to visualize key metrics and KPIs related to data pipelines and data quality. Tools like Grafana or Tableau can be helpful for this purpose. Historical data. Store historical monitoring and logging data to identify trends and patterns over time. Historical data can also be useful for capacity planning and forecasting. Automation. Automated remediation. Implement automated actions or remediation steps in response to detected issues, reducing manual intervention and downtime. Autoscaling. Use auto-scaling mechanisms to dynamically adjust resources, example, compute power, based on workload and performance metrics. Documentation. Maintain comprehensive documentation for data pipelines, logging configurations, and monitoring setup. This documentation helps new team members understand the system and troubleshoot issues effectively. In conclusion, data monitoring and logging are essential components of data engineering that ensure the reliability and performance of data pipelines and systems. These practices enable early detection of issues, timely responses to anomalies, and continuous improvement of data quality and system performance. Data scalability in data engineering refers to the ability of a data system or architecture to handle increasing amounts of data while maintaining performance, reliability, and cost-effectiveness. As organizations generate and collect more data, it's essential to design data engineering solutions that can scale seamlessly to accommodate this growing data volume. Here are some key aspects of data scalability in data engineering. Horizontal scalability. This involves adding more machines or nodes to a system to increase its capacity. Horizontal scalability is crucial for data systems because it allows you to distribute data and processing across multiple servers or clusters. Common technologies used for horizontally scalable data storage include distributed databases like Apache Cassandra, Hadoop HDFS, and cloud-based storage solutions. Vertical scalability. Vertical scalability involves increasing the resources, CPU, memory, storage, of an individual machine or server. While it can be beneficial to some extent, it may not be as cost-effective or practical as horizontal scalability when dealing with massive amounts of data. Vertical scalability may be appropriate for smaller datasets or when the system has room for expansion. Data partitioning and sharding. When dealing with large datasets, it's common to partition or shard the data. This involves dividing the data into smaller, manageable pieces, which can be distributed across multiple servers or nodes. Data sharding strategies can be based on various criteria, such as range-based, hash-based, or location-based, depending on the use case. Load balancing. Distributing incoming data processing requests evenly across multiple servers or nodes helps prevent bottlenecks and ensures efficient resource utilization. Load balancers play a crucial role in achieving this by directing traffic to the appropriate resources. Cluster computing. Leveraging cluster computing frameworks like Apache Hadoop and Apache Spark allows you to process large datasets in a distributed and parallelized manner. These frameworks are designed to scale horizontally, making them well-suited for big data processing tasks. Data pipeline scalability. Data pipelines, which are responsible for data ingestion, transformation, and loading, ETL, must be designed with scalability in mind. This includes using scalable data integration tools and frameworks and implementing best practices for data pipeline orchestration. Cloud services. Cloud providers offer scalable data storage and processing services, such as AWS S3, Azure Data Lake Storage, and Google BigQuery. These services allow organizations to scale their data infrastructure as needed, paying only for the resources they use. Caching and indexing. Implementing caching mechanisms and efficient indexing strategies can help improve data retrieval performance, especially when dealing with large datasets. Monitoring and auto-scaling. Implement robust monitoring solutions to track system performance and resource utilization. Auto-scaling mechanisms can automatically adjust resources based on predefined thresholds or triggers to ensure that the system remains responsive and cost-effective. Cost optimization. As data scales, so does the cost of storage and processing. It's important to continuously optimize costs by using data lifecycle management strategies, such as data archiving and tiered storage, to reduce unnecessary expenses. In conclusion, data scalability is a critical consideration in data engineering to ensure that systems can handle the ever-increasing volumes of data efficiently and effectively. It requires a combination of architectural choices, technology selection, and best practices to build scalable data solutions that meet the evolving needs of an organization. Data engineers use a variety of tools and technologies to build and maintain data pipelines, data warehouses, and other data infrastructure. Some of the most popular data tools and technologies used in data engineering include programming languages. Python and SQL are the two most popular programming languages used in data engineering. Python is a general-purpose language that is well-suited for data manipulation, analysis, and visualization. SQL is a database query language that is used to extract and transform data in databases. Data warehousing and big data processing. Apache Spark is a popular open-source unified analytics engine for large-scale data processing. It can be used to process both structured and unstructured data from a variety of sources. Apache Hive is another popular open-source tool that is used to query and analyze large datasets stored in Hadoop Distributed File System, HDFS. Data storage. Cloud data warehouses like Amazon Redshift and Google BigQuery are popular choices for storing and analyzing large datasets. They offer high scalability and performance, and they can be accessed from anywhere in the world. Data orchestration. Apache Airflow is a popular open-source workflow management platform that is used to automate the execution of data pipelines. It allows data engineers to define and schedule complex data processing workflows. Data visualization and business intelligence. BI Tableau, Power BI, and Looker are popular BI tools that allow data engineers and analysts to create interactive dashboards, reports, and visualizations to explore and analyze data. In addition to these general-purpose tools and technologies, data engineers also use a variety of specialized tools for specific tasks, such as data quality assurance, data governance, and machine learning. Here are some examples of how data tools and technologies are used in data engineering. Python. Python is used to write data pipelines, transform data, and perform data analysis. It is also used to develop machine learning models. SQL. SQL is used to query and transform data in databases. It is also used to create data warehouses and data lakes. Apache Spark. Apache Spark is used to process large datasets from a variety of sources. It is also used to develop machine learning models. Apache Hive. Apache Hive is used to query and analyze large datasets stored in HDFS. Amazon Redshift. Amazon Redshift is used to store and analyze large datasets in the cloud. Google BigQuery. Google BigQuery is used to store and analyze large datasets in the cloud. Apache Airflow. Apache Airflow is used to automate the execution of data pipelines. Tableau. Tableau is used to create interactive dashboards, reports, and visualizations to explore and analyze data. Power BI. Power BI is used to create interactive dashboards, reports, and visualizations to explore and analyze data. Looker. Looker is used to create interactive dashboards, reports, and visualizations to explore and analyze data. Data tools and technologies are constantly evolving, and new tools are emerging all the time. Data engineers need to stay up to date on the latest trends and technologies in order to be effective in their roles. Data versioning and continuous integration, continuous deployment, CI/CD, are essential practices in data engineering to ensure data pipelines are reliable, reproducible, and can be deployed with confidence. Here's an overview of both concepts and their application in data engineering. Data versioning. Data versioning is the process of tracking and managing changes to datasets, code, and configuration files used in data pipelines. It's crucial for maintaining data quality, traceability, and reproducibility. Here's how data versioning is applied in data engineering. Version control system. VCS. Use a VCS-like Git to track changes to your code, SQL scripts, and configuration files. This allows you to maintain a history of all modifications, collaborate with team members, and roll back to previous versions if needed. Data versioning tools utilize tools and platforms designed for data versioning, such as DVC, Data Version Control, or Delta Lake, for structured data. These tools enable versioning of data files and ensure that data remains consistent and can be rolled back to previous states. Documentation. Maintain detailed documentation about data versions, including data source information, transformations, and any changes made in each version. Metadata management. Implement metadata management solutions to track changes to schema, data lineage, and metadata. Tools like Apache Atlas or Amundsen can help with this. CI/CD in data engineering. CI/CD practices help ensure that your data pipelines are built, tested, and deployed in a systematic and automated manner. This reduces the risk of errors and enables faster development and deployment cycles. Continuous integration, CI. Automated testing. Set up automated tests for data pipelines to ensure data quality, consistency, and accuracy. Common tests include schema validation, data validation, and statistical checks. Code reviews. Use code reviews to maintain code quality and ensure that changes do not introduce errors or issues. Continuous deployment, CD. Deployment automation. Automate the deployment of data pipelines using tools like Apache Airflow, Luigi, or DBT, Data Build Tool. This ensures that code and configurations are consistently deployed across environments. Environment promotion. Promote data pipeline changes through different environments, such as development, staging, and production, with controlled and automated processes. Monitoring and alerting. Implement monitoring and alerting systems to detect issues in production pipelines. Tools like Prometheus and Grafana can be used for this purpose. Rollbacks. Have a process in place for rolling back changes in case of issues or errors in production. Containerization and orchestration. Utilize containerization, example, Docker, and orchestration, example, Kubernetes, to manage the deployment and scaling of data pipelines, making them more portable and scalable. Infrastructure as code. IAC. Define your data infrastructure using IAC tools like Terraform or AWS CloudFormation, allowing for the automated provisioning and management of resources. Versioned environments. Ensure that your environments, development, staging, production, are versioned and consistent to avoid discrepancies between them. By implementing data versioning and CI/CD practices in data engineering, you can maintain data pipeline quality, ensure repeatability, and streamline the development and deployment process. This leads to more reliable and agile data engineering workflows. Data architecture patterns are high-level, reusable design approaches or solutions for structuring and organizing data within an organization. These patterns are critical for designing data systems that support business needs and enable efficient data management, storage, processing, and analysis. Here are some common data architecture patterns. Batch layer and speed layer. Batch layer. This layer is responsible for processing large volumes of historical data, typically using batch processing frameworks like Hadoop. It is well suited for complex transformations, data cleaning, and aggregations. Speed layer. This layer deals with real-time or near-real-time data processing using stream processing frameworks like Apache Kafka or Apache Flink. It complements the batch layer by handling recent data. Lambda architecture. Combines the batch layer and speed layer into a single architecture. It provides both batch and real-time processing capabilities, enabling consistent and accurate results for data analytics. Data warehousing. A centralized repository for structured data that allows for querying and reporting. Data warehousing architecture patterns include Kimball and Inman, which offer different strategies for data modeling and ETL, extract, transform, load, processes. Data lake architecture. Data lakes store data in its raw form and are not limited to structured data. Data is ingested, cataloged, and can be processed on an as-needed basis. Common technologies used in data lake architectures include Hadoop HDFS and cloud-based solutions like AWS S3 or Azure Data Lake Storage. Event sourcing. This pattern captures changes to data as a series of immutable events. It is commonly used in systems where auditing and traceability are critical, such as financial applications or content management systems. Microservices architecture. In this pattern, data is managed independently by microservices. Each microservice has its data store, which can be a relational database, NoSQL database, or other storage solutions. This pattern promotes scalability and agility. Polyglot persistence. This approach involves using different database technologies for different data needs. For example, using a relational database for structured data and a NoSQL database for unstructured or semi-structured data. Data virtualization. Data virtualization allows data to be accessed and presented as if it were in a single database or store, even when it is distributed across multiple sources. It abstracts the physical location and format of data. Federated data architecture. In this pattern, data remains in its source system, and a centralized system queries and aggregates data from different sources in real time, providing a unified view. Data mesh. This is an emerging data architecture pattern that emphasizes decentralization and domain-oriented ownership of data. Data mesh aims to address challenges related to scalability, data discovery, and data product delivery in large organizations. Data governance and security patterns. These patterns focus on implementing data governance and data security measures to ensure data quality, compliance, and protection. Patterns include data lineage, access control, encryption, and auditing. Data integration patterns. These patterns deal with connecting and integrating data from various sources. Patterns like extract, transform, load, ETL, change data capture, CDC, and data synchronization fall under this category. These data architecture patterns can be combined or adapted to suit the specific needs and requirements of an organization's data environment. The choice of patterns depends on factors such as data volume, velocity, variety, business objectives, and the technology stack in use. Effective data architecture patterns support data-driven decision-making and enable organizations to derive valuable insights from their data assets. Data migration and replication are two important concepts in the field of data engineering, particularly when dealing with databases and data storage systems. These processes are essential for ensuring data availability, consistency, and scalability in various data management scenarios. Data migration. Data migration is the process of transferring data from one location or data storage system to another. This can involve moving data from one database to another, from on-premises storage to the cloud, or between different types of data stores. Data migration is typically carried out for several reasons, including system upgrades, hardware replacement, or consolidating data from multiple sources into a single repository. Key considerations for data migration. Data integrity. Ensuring that data remains accurate and consistent during and after migration. Downtime, minimizing or eliminating downtime during the migration process, especially in critical systems. Data transformation, converting data to fit the target schema or format. Validation, verifying the success of the migration by comparing the source and destination data. Common tools for data migration include ETL, extract, transform, load, processes, migration scripts, and specialized data migration software. Data replication. Data replication involves creating and maintaining duplicate copies of data in real-time or near real-time across multiple storage systems or databases. The primary purpose of data replication is to ensure data availability, fault tolerance, and improved performance. Replication can be either synchronous, data is updated in real time across all copies, or asynchronous, data is updated with a delay. Key use cases for data replication. High availability, ensuring that data is accessible even in the event of system failures or outages. Load balancing, distributing read queries across replicas to improve query performance. Disaster recovery, having backup copies of data in geographically distributed locations. Analytics, providing data for reporting and analytics without impacting the primary database. Replication can be one-way, from a source to one or more targets, or bidirectional, between multiple sources and targets. Different databases and storage systems have their own mechanisms for setting up and managing data replication, such as master-slave replication, peer-to-peer replication, or log shipping. Data engineering tools. Data engineers often use a combination of tools and technologies to implement data migration and replication, including ETL tools, such as Apache NIFI, Talend, or Apache Spark, which are used for data extraction, transformation, and loading during migration. Database replication tools, specific to database management systems, such as PostgreSQL streaming replication or tools like Apache Kafka for event-driven data replication. Cloud services, cloud platforms like AWS, Azure, and Google Cloud offer various services and tools for data migration and replication. Change data capture, CDC technologies that capture and replicate changes in data, often used in real-time replication scenarios. In summary, data migration and replication are fundamental processes in data engineering, with migration involving the movement of data from one location to another, and replication involving the maintenance of synchronized copies of data across multiple systems. The choice of approach and tools depends on the specific requirements of your data management needs, including data availability, scalability, and fault tolerance. Star schema and snowflake schema are two common data modeling techniques used in the design of data warehouses and data marts. They are both designed to optimize the performance of querying and reporting on large datasets, but they differ in their level of normalization and complexity. Star schema. Overview. The star schema is a simple and denormalized data modeling approach in which a central fact table is connected to dimension tables. It resembles a star when visualized, with the fact table in the center and dimension tables surrounding it. Fact table. The fact table contains quantitative data, such as sales figures, quantities, or other metrics. It is typically at a lower level of normalization and often includes foreign keys to link to dimension tables. Dimension tables. Dimension tables store descriptive attributes related to the data in the fact table. Examples of dimension tables in a retail scenario might include product, customer, time, and store. These tables provide context for the data in the fact table. Advantages. Simplifies queries and makes them more intuitive. Offers excellent query performance because of denormalization. Easier to understand for end users and analysts. Disadvantages. Data redundancy is present due to denormalization. Maintenance can be more complex as data changes. Snowflake schema. Overview. The snowflake schema is a more normalized and complex version of the star schema. In this approach, dimension tables are further normalized into subdimensions, resulting in a structure that resembles a snowflake when visualized. Fact table. Like the star schema, the fact table contains quantitative data. Dimension tables. Dimension tables are highly normalized and are often broken down into multiple related tables. For instance, a product dimension in a snowflake schema might be broken down into separate tables for product category, product subcategory, and product. Advantages: reduces data redundancy and saves storage space. Easier to maintain and update dimension data. Ideal for scenarios where data updates are frequent. Disadvantages: more complex to query, as it often requires multiple joins to retrieve data. Query performance may be slower than a star schema, especially for complex queries. Choosing between star and Snowflake schema. The choice between star and Snowflake schema depends on your specific requirements and trade-offs. Use a star schema when query performance and simplicity for end users are top priorities, and data updates are less frequent. Use a Snowflake schema when data updates are frequent, and you need to save storage space and have a more manageable approach for maintaining dimension data. In practice, a hybrid approach may also be used, where some dimension tables are denormalized, star-like, while others are more normalized, Snowflake-like, depending on the characteristics of the data and the analytical needs of the organization. Data catalog and metadata management are crucial aspects of data engineering and data governance. They play a significant role in ensuring that data is discoverable, understandable, and effectively utilized across an organization. Here's an overview of these concepts. Data catalog. A data catalog is a centralized repository that stores metadata about the data assets within an organization. This metadata includes information about the data's structure, location, lineage, ownership, and usage. The primary functions of a data catalog are: data discovery. It allows users to search for and discover data assets within an organization. This is essential for data analysts, data scientists, and business users to find the data they need. Data lineage. It provides information about the origin and transformation of data, helping users understand how data flows through the organization and how different datasets are related. Data usage and access. Users can see who has access to the data and how it is being used. This is crucial for data governance and compliance. Metadata management. It stores metadata related to data assets, including descriptions, data quality, and data classification. This helps users understand the data's meaning and quality. Collaboration. Data catalog tools often support collaboration features, enabling data users to comment, rate, and share insights about data assets. Data governance. Data catalogs play a vital role in data governance by enforcing data access policies, data stewardship, and ensuring compliance with regulations. Metadata management. Metadata is data about data. In the context of data engineering, metadata management involves collecting, storing, and managing metadata related to all aspects of data, including its source, structure, transformations, usage, and lineage. The goals of metadata management are: data understanding. Metadata helps users understand what the data means, where it comes from, and how it's structured. Data lineage. It tracks the history of data, showing how it has been transformed from source to destination. Data quality. Metadata can include information about data quality metrics and indicators, helping organizations assess and improve data quality. Data governance. Metadata management is crucial for enforcing data governance policies, data classification, and ensuring compliance with regulations. Data integration. Metadata aids in the integration of data from various sources by providing a common understanding of data elements. Data security. Metadata can include access controls and security information, helping to protect sensitive data. In a data engineering context, metadata is often generated and captured as part of the ETL, extract, transform, load, process. Metadata is stored in a metadata repository, which can be part of a data catalog or a separate system. Effective data catalog and metadata management are essential for organizations to leverage their data assets efficiently, ensure data quality, maintain data governance, and enable data-driven decision-making. These tools and practices are especially important as data volumes and complexity continue to grow. Data governance and compliance are critical aspects of data engineering, ensuring that organizations collect, store, process, and utilize data in a responsible, secure, and compliant manner. Let's explore these concepts in more detail. Data governance. Data governance refers to the overall management of data within an organization. It encompasses a set of policies, procedures, and practices that ensure data quality, consistency, security, and usability. In the context of data engineering, data governance involves several key components. A. Data quality, ensuring that data is accurate, complete, and reliable. Data engineers often create processes to cleanse and transform data to maintain its quality. B. Data security, implementing measures to protect data from unauthorized access and breaches. This includes encryption, access controls, and auditing. C. Data cataloging and metadata, creating a catalog of data assets and metadata, information about data, to help users find and understand data. D. Data lifecycle management, defining how data is created, stored, used, and eventually retired. This involves data retention policies and archival processes. E. Data stewardship, assigning responsibilities to individuals or teams for data management, including defining who is responsible for different aspects of data. F. Data lineage and traceability, tracking the flow of data to understand where it comes from, how it is transformed, and where it is used. This is crucial for compliance and auditing. Compliance. Data engineering must adhere to various legal and regulatory requirements, depending on the industry and location. Compliance ensures that organizations handle data ethically and legally. Common data compliance frameworks and regulations include A. GDPR, General Data Protection Regulation applicable to organizations handling European Union citizens' data. GDPR enforces strict rules regarding data privacy, consent, and the right to be forgotten. B. HIPAA, Health Insurance Portability and Accountability Act regulates the handling of healthcare data in the United States, emphasizing data security and patient privacy. C. PCI DSS, Payment Card Industry Data Security Standard applies to organizations that process credit card payments, setting requirements for secure cardholder data storage and transmission. D. Sarbanes-Oxley Act, SOX regulates financial data and reporting, ensuring the accuracy and transparency of financial records. E. CCPA, California Consumer Privacy Act. Similar to GDPR, it governs data privacy for California residents. Data engineering for compliance involves data classification, identifying and categorizing data based on its sensitivity to apply appropriate security measures. Access control, implementing role-based access controls and auditing to ensure data is only accessible to authorized personnel. Data encryption, encrypting data at rest and in transit to protect it from unauthorized access. Auditing and monitoring, keeping detailed records of data access and changes for compliance audits. Data retention and deletion, implementing policies to manage the life cycle of data, including its eventual deletion as required by regulations. Data impact assessments, assessing the potential impact of data processing on privacy and compliance and mitigating risks. In summary, data governance and compliance in data engineering are essential for organizations to responsibly and legally manage their data assets. This involves a combination of technical and organizational measures to ensure data quality, security, and compliance with relevant regulations. Scalable data storage solutions are crucial in data science to handle the growing volume, velocity, and variety of data generated and analyzed. These solutions enable data scientists to access, store, and process large datasets efficiently. Here are some scalable data storage solutions commonly used in data science. Distributed file systems. Hadoop Distributed File System, HDFS. HDFS is the distributed file system used in the Hadoop ecosystem. It is designed to store and manage large volumes of data across a cluster of machines. It provides fault tolerance, data replication, and efficient data processing with MapReduce. NoSQL Databases. Apache Cassandra. Cassandra is a highly scalable NoSQL database designed for handling large amounts of data across distributed clusters. It is suitable for time series data and provides high availability and fault tolerance. MongoDB. MongoDB is a document-oriented NoSQL database that can scale horizontally to accommodate large datasets. It is suitable for semi-structured and unstructured data. Couchbase. This NoSQL database is known for its high performance, scalability, and support for caching. It's often used for real-time data processing and caching. Data warehouses. Amazon Redshift. Redshift is a fully managed data warehouse service provided by AWS. It can handle large-scale data analytics with high performance and scalability. Google BigQuery. BigQuery is Google Cloud's serverless, highly scalable data warehouse solution, ideal for running SQL queries on large datasets. Object storage. Amazon S3. Amazon Simple Storage Service, S3, is a highly scalable object storage service. It's often used to store and retrieve data for data science projects. It can store both structured and unstructured data. Google Cloud Storage. Google Cloud Storage is Google's object storage solution, providing scalability and integration with other Google Cloud services. Columnar databases. Apache Parquet. Parquet is an open-source columnar storage format. It's not a database itself but is often used with data processing frameworks like Apache Spark and Hive for efficient storage and querying of large datasets. Apache Arrow. Arrow is an in-memory columnar data format and processing framework that aims to provide efficient data interchange between systems. It's designed for large-scale data analytics. Data lakes. AWS Data Lake. AWS provides a solution for building data lakes using services like S3, Glue, and Athena. Data lakes allow the storage and analysis of both structured and unstructured data at scale. Azure Data Lake Storage. Microsoft Azure offers a data lake storage solution that integrates with various data processing and analytics services. Distributed databases. Google Spanner. Spanner is a distributed, globally scalable database system. It combines the benefits of traditional relational databases with NoSQL features and global distribution. Elasticsearch. Elasticsearch is a real-time, distributed search and analytics engine. It's often used for text and log data analysis and can be scaled to handle large datasets. When selecting a scalable data storage solution for data science, consider factors such as data volume, data variety, budget, integration with existing tools, and the specific requirements of your data science projects. The choice of the right solution depends on the nature of the data and the analytical workloads you need to support. Data backup and disaster recovery are critical components of data engineering that ensure the continuity and integrity of an organization's data in the face of unexpected events or disasters. Here's an overview of these concepts. Data backup. Data backup is the process of making copies of your data and storing them in a separate location. The primary purpose of data backup is to safeguard data against various risks, such as hardware failures, accidental deletions, data corruption, and cyber attacks. Key aspects of data backup include regular backup schedule. Establish a routine backup schedule based on the criticality and frequency of data changes. Common backup strategies include daily, weekly, and incremental backups. Data retention policies. Define how long backups are retained. This involves balancing the need for historical data with storage costs and compliance requirements. Backup methods. Choose appropriate backup methods, including full backups, entire datasets, incremental backups, only changes since the last backup, and differential backups, changes since the last full backup. Off-site and cloud backup. Storing backups in off-site locations or cloud services adds an extra layer of protection against on-premises disasters. Data encryption. Encrypting backups is essential to protect sensitive information in transit and storage. Testing and verification. Regularly test and verify the integrity of backups to ensure they can be restored when needed. Disaster recovery. Disaster recovery involves a set of strategies, policies, and procedures to restore data and IT systems in the event of a major disruption or disaster. Disasters can include natural events like floods or earthquakes, as well as human-made disruptions such as cyber attacks or system failures. Key components of disaster recovery in data engineering include recovery time objective, RTO. Determine the acceptable downtime for different systems and datasets. This helps prioritize recovery efforts. Recovery point objective, RPO. Define the maximum allowable data loss in case of a disaster. It determines the frequency of backups and data recovery points. Data replication. Implement data replication strategies to maintain copies of data at geographically separate locations. This can include real-time replication or near real-time replication for critical systems. Failover systems. Set up failover systems or hot standby systems that can quickly take over when the primary system fails. Backup sites. Establish backup data centers or cloud-based disaster recovery sites where critical applications and data can be restored. Incident response plan. Develop a clear and well-documented incident response plan that outlines roles, responsibilities, and procedures for various disaster scenarios. Regular testing and drills. Test disaster recovery procedures through regular drills and simulations to ensure preparedness. Data loss prevention. Implement data loss prevention strategies to protect against data corruption or loss during disasters. It's important for organizations to strike a balance between the costs associated with backup and disaster recovery solutions and the potential impact of data loss and downtime. The specific backup and disaster recovery strategies will vary depending on the organization's needs, the criticality of the data, and regulatory requirements. Moreover, it's essential to update and adapt these strategies as technology and data environments evolve.